So this is the third part of the recitation, and here I am talking about Lorentz transformations. I don't know how much of this stuff you're going to need for this course, but I think it's quite important to discuss. So what we had in classical mechanics is that we had Galilean transformations. And this is a really basic idea that if one frame does not move at all, and if the other just moves in any other direction, let's say it moves in the x direction of the not moving inertial frame with the speed nu. So here what happens is that it doesn't matter though if we have some other complex motions, because we can always rotate and orient these frames so that they move. The S primed frame always moves in the x direction of the stable frame. So it just does not matter the direction. So what happens is that we are trying to measure distance in the S prime frame, and we are measuring distances in every direction. So we are going to relate those to the S frames measurements. So what happens in the good old mechanics is that the time is universal. So we have this, and what's going to happen is that as we are measuring some distance in primed frame, the prime frame itself is going to move by speed nu and time t. So what we are going to measure is this. Hence, we are going to just write in the primed frame x minus t is how we measure distance in the x direction. And since we do not move, the primed frame does not move in the other directions, we just write them like this, and we know we have universal time. So these are the Galilean transformations. But what happens in the special relativistic case? What happens is that this doesn't hold, really. This doesn't hold at all. So what happens is that we have studied this before. We have this time dilation formula, which is great, and just we're going to put this right there. Let me not write anything wrong. Okay. We have t comma t0. All right. So what we have here is that now this is the time. This is dilated. So what we had is more openly, this one, c square, and we had said that this is always bigger than t0. So in the frame that is moving. So we are going to just write that this way. Now, but what we do not actually know is that how are we going to relate these two in terms of other distances. Alright, so since we do not move in these two frames, we don't move the z and y directions, we do not move in them. We just establish this, and these are here to stay. Alright, so but what actually happens in the x direction is that we had here, we had this. Okay. Now this is going to be actually contracted, because since we're moving, the length has to be contracted by some factor of gamma. Right. So we know actually how to derive other stuff then. Now we have established this too. We can actually relate the time. So time in the moving frame is going to be measured like this. X c squared gamma. How do we actually derive this? Now let me have another page, and then we are going to write this. All right, this is so this is what we had from the length contraction. All right, so we are going to eliminate x prime. So like we had this x prime, so, and we can in fact write x as this one, as this is going to give us, like, thinking about the s prime as the frame that doesn't move, and s to be the frame that moves with the minus new velocity. So this all makes sense. So we are going to, in order to get t, we are going to eliminate those in between each other. So how are we going to do this is quite basically like we're going to pick one and stick it into the other. So let me pick this one, and let me write this minus t. So square x minus okay, wait a second. So how we going to do this is like this plus t, and this is square x minus v square new t minus gamma new t. This is x, and we're going to eliminate the x by putting it here. So it's going to be like this, x minus t minus t. All right, so, and we are going to just move forward with this to write t minus v square. See, so I'm not gonna go into all this algebra mumbo jumbo, because it's basically what you do is to put x to one side, just write those openly and get some factors here and there and obtain this equation. So we also can invert this, thinking that the other frame is moving in the other direction, right? See, all nice and dandy. So what we had, to summarize, what we had was this. We had x plus or minus x prime minus ut, and y prime was the same, z prime was the same, t prime was the same. Now this was Galilean transformations, and our Lorentz transformations happen to be this. So this is great. What this actually does is that we just measure everything in our own frame, write it down, then go ask our friend, what was your speed? Were you inertial? And they tell you some speed. So you get that number, write that number down, stick it into this, and actually know exactly what your friends observed. So this was the Lorentz transformation part.